A plane with the unlikely name, the Mango, the Transavia PL-12 M300. This little utility, with military applications as an ambulance, a spotter and a communications aircraft, is an adventurously designed and highly distinctive-looking modern aeroplane. Why does it look like it does? For example, what virtues do the twin booms have that the designer employed them? The fuselage shortened high, and the little second wing with the undercarriage, how did they get like that? It's not a conventional-looking aeroplane at all, yet, despite being a piston-engined aircraft, it doesn't look like a relic of a bygone age. Obviously, everything about any aircraft design is settled by the designer's choice to complement the overall success of the plane. Functional considerations will decree that a transport will have different attributes from a fighter. The Mango is an unrestrainedly functional design which serves its aerial jeep role very well. Yet it's actually a mutation, being derived from a plane which was designed for a totally different role. At Transavia's factory in Sydney, Australia, variations on the PL-12 have been developed and refined around a basic design that's proved very adaptable and reliable. The PL-12s are extremely simply constructed, very robust and easy to service. There has been a presiding consideration to have the little plane be as practical to operate as possible. It's lightweight, yet sturdy. Its simplicity of construction is the result of a lot of complicated and exact calculation and consideration. Its original configuration was as an agricultural aircraft, as a crop duster, seeder, firefighter. It's not super fast, but it doesn't need to be. However, it is agile, responsive, and a delight to its pilots, because if you're going to buzz around feet off the ground, dodging trees, fences, and barns, then you need a plane that cooperates in keeping you alive. The Sky Farmer agricultural aircraft, as the original PL-12 air truck developed, was constructed around a large hopper, and the design variant was dictated to by the practical concerns of effectively operating as a crop duster. The hopper had to be easy to fill, and the plane capable of operating from unprepared strips. As an industrial tool, reliable continuous operation would be needed for cost-effective use, as would a long life expectancy. To a large extent, as a special-purpose aircraft, the design is ageless. The task has been addressed directly, and the results are a sort of optimum. This little plane does its job very well. It's no doubt fortuitous for its manufacturer that the design has proved as impressively flexible as it has, but it is, for consideration of the Sky Farmer, not as important as the plane's success at its dedicated task. One aspect of the plane that shows the degree of design sophistication revolves around the little stub wings. All aircraft generate vortices around their wingtips, and these would be valuable in dispersing the sprays or fertilizers spread by a crop duster, but with a normal layout, they're too far out to have any effect. With the PL-12, the vortices around the end of the stub wings feed the outer wing vortices and serve to give the little plane a very wide sweep with each pass. In addition, of course, the stubs give extra wing surface and lift, and give a variation of the sort of controllability associated with small biplane aircraft, enhancing the little plane's enviable agility. The Sky Farmer is a successful modern aeroplane, admittedly a very unusual looking one. This is also an aircraft. I say this because it's not immediately apparent at all that this mess of scaffolding and wheels is designed to take to the air. particularly when it's perched on top of a pole. However, this is the German VFW Corporation's SC-1262 hover rig, a test aircraft conducted as part of the development of the VAC 191, an ultimately unsuccessful vertical takeoff fighter design which employed both the vectored thrust of its main engine and the lift of two dedicated engines pointing down out of the fuselage. The hover rig was constructed to allow work on systems to give the pilot of the VAC some control of the plane when it was in hover and its normal flight control surfaces were neutralized. A distinctly strange and almost comically unlikely looking aircraft. But the hover rig was constructed to conduct serious experiments, and the history of flight is constructed with such test programs. It's unlikely that much of interest to an aircraft engineer was gleaned in finding out how many men could fit into the engine compartment of an F-80. But putting ramjets on the wingtips can make the same type of aircraft a seriously interesting test bed. The ramjet, with no moving parts and a theoretical infinite power output, has fascinated aircraft designers, offering much and as a result being tested extensively. Here, obviously, the power output is not on trial. Any attempt to wind these ramjets out would rip the wings off the F-80 as though they were perforated toilet paper, well before the engine chambers melted. Instead, the fighter allows the engines to be brought up to operating speed and, within the limitations of the airframe, the engines can then demonstrate that they work. Where this testing is fairly limited and unsophisticated, ramjets have been at the heart of some very highly sophisticated tests. And one of these, the Lockheed X7 project, serves to give an insight into how designers work. In part, it's interesting because it was Lockheed's first step into pilotless planes. But it's also important in the history of modern missilery and the development of ramjet engines. Lockheed's famous designer, Kelly Johnson, outlines the beginnings of the program.
Just after the war, when the United States was getting into its guided missile program, Lockheed had to evaluate what part it could take in such a program. We felt we were primarily an airframe manufacturing organization, and at the time did not think that we had capabilities in the field of radar and guidance that were necessary to complete an overall guided missile program. Sometime before, we had established a procedure whereby, with a very few good men, we were able to design and build the F-80 Shooting Star in 141 days. The basic philosophy of the Lockheed Company, which reflected so strongly in this performance, has been carried forward naturally through the X7 project. The application of this philosophy has proven that a few well-qualified people can produce more per year and more per dollar than a larger group of less qualified people having the attendant large organizational and operational problems.
Ben Rich joined the aerodynamics and thermodynamics department of Lockheed and worked first on the propulsion system for the F-104. On the U-2 and SR-71, he worked on the overall airplane design. I have no question but that the future of the Skunk Works is in very good hands under Ben Rich.
Well, the whole principle of the Skunk Works with Kelly is based on three things. Kelly believes in integrity, responsibility, and authority. And integrity is the one thing that Kelly has really stressed in the Skunk Works. You don't build anything you don't believe in. And Kelly's illustrated this many times at the Skunk Works. We had a contract many years ago to build a liquid hydrogen airplane going, 2.5 at 100,000 feet. And the airplane was going to turn out to be an aerodynamic, wide-bodied dog. And Kelly went back to the Air Force and returned the $96 million that he had. Now, we have another axiom in the Skunk Works that if it works, don't fix it. Keep it simple, the KISS theorem. Keep it simple and stupid. If you make the things that a college professor with a PhD has to run it, it won't work. We design, we implement, we prototype, we put it in production, and we follow the entire program from its birth to its death. And there are very few people in this world who have that opportunity.
The design of the X7 could have taken any of a number of forms, but these were sorted through, and after extensive consideration and assessment, the final configuration was settled. That shape had then to be refined, and the ancillary systems for its use sorted out. In some cases, entirely new answers were found for old problems because of the specific nature of the testing to be conducted. Wherever possible, the design team worked to keep the expense of the program down, and many aspects were sorted out in miniature, in wind tunnels, or as here with rockets, to confirm or sometimes debunk the designer's theories. Back in the late 40s, there were no digital computers around to test theory in the abstract. One example of the design challenge in the system is that the Lockheed team had to come up with a new parachute system to operate effectively when the X7 was traveling at supersonic speeds. Once again, in the interests of economy, a stage of preliminary testing employed 1/3 scale models to provide data on roll stability, lift, drag, and separation behavior. Making the scale examples not only allowed economy in construction, but permitted the use of a P-38 Lightning as a mothership for the test flights. The whole area of remotely controlled but autopiloted aircraft was in its infancy, not only a new field for Lockheed. The X7 was not a target-seeking missile, but its development required the creation of very complex electronics in the autopilot, preset flight program director, and ground-operated remote controls operating through a radar link. A complete telemetry system had to be devised to log test data, together with a host of other peripheral electronics and recorders. The Lockheed team were designing not only the aircraft, but the whole experimental system's hardware to monitor and assess its performance. With the first X7s constructed and the test systems developed, the actual series could commence. The aim of the program was to assess the viability of ramjet engines, then largely an area of theory rather than established practice. Engines of this type had been incorporated into the design of the Bomark missile, and the X7 was to be the test bed to assess these engines in hypersonic flight.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Around 80 successful test flights were conducted with the X7 and its later developments out of a total of over 130, and a bewildering variety of problems were encountered during the series. These included radar control and autopilot failure, human error in the operation of the complicated ground systems, and some design problems, both ergonomic and aerodynamic. However, the missile's superb performance record eventually became an item of significant pride to Lockheed. Along the way, the X7s consistently revealed failings in the Marquardt company's ramjets, and it was the availability of these sturdy and reliable Lockheed test drones that afforded the hard data which was needed for the refinement of the ramjets into usable power plants. Typical of the X-7's simple yet practical problem solving was the fact that it was designed to land, if that's the word, by driving the specially hardened nose spike into the ground and stand like a pillar, waiting the ground retrieval crews, who carted it back to be refurbished in preparation for its next mission. There were over 60 X-7 aircraft, including some designated XQ-5s, which were designed to be used as high-speed target drones. Now, although there were some spectacular crashes in the test series, the target drones proved to be relative failures in their allotted role because they were almost impossible to shoot down. They were too fast. The X-7s had by then proved capable of very high speeds, with the top speed achieved being Mach 4.31, 2,881 miles per hour, and their performance proved significantly higher than that of the surface-to-air weapons they were designed to test. This was acutely embarrassing to the various government agencies and manufacturers involved in the weapons systems. There are many uses for pilotless aircraft, and being target practice for new weapons or for new pilots is one of them. Pretty obviously, the job of pilot on a target that's to be blown out of the sky by a missile is one that there would be very few applicants for. Despite their disposable nature, target drones must be well-built and designed aircraft, with complete internal controls and stability and a handy turn of speed. They present a perhaps unglamorous but very challenging design task to the aviation engineer. Perhaps more rewarding to the designer is to be involved in a project like the HIMAT drone. HIMAT stands for Highly Maneuverable Aircraft Technology, and the aim of the series was in part to address and defeat the so-called stall barrier, limiting the angle of attack that a plane may adopt, to free fighter pilots further in aerial combat. The project was carried out by the Rockwell Corporation, and the drone is actually a host of very advanced aeroplanes. The HIMAT consists of an advanced jet core aircraft, to which can be affixed different arrangements of wings, canards, tails, engine inlets, and jet nozzles. Thus, a large number of combinations can be tried out, and the advantages, disadvantages, and relationships within various settings can be studied. An enormous amount of very expensive prototype production and testing has been accomplished with the one aircraft, not only saving money, but compressing years and programs into a very successful single test series. The internal coherence of the results obtained has informed the follow-on multinational X-31 fighter project. Like the X-7, the HIMAT drone has been involved at the cutting edge of the technology of its day in the development and testing of new aviation design and hardware. However, drone aircraft have developed over most of aviation's history, and their design evolution has branched repeatedly, so that today they play many different roles. For example, during World War I, the United States saw the development of the first flying bomb. These tests of the plane known as the Bug were conducted under the technical supervision of Orville Wright, and significantly, one of the young officers involved was Hap Arnold. The involvement of these illustrious names did not guarantee the program against failures. The little biplane did work occasionally, but its military significance was more in what it heralded rather than in any damage it may have been capable of causing itself. By the 1930s, when this little target drone was developed, one of the Bug's major deficiencies, its lack of guidance, was being looked at. Like today's model planes, the aircraft obeyed a handheld radio control unit. Interestingly, this unit employed a telephone dial to send the selected signal to the drone. As with all target drones, there was a balance between the disposability of the aircraft and the sophistication necessary for it to do its job. And in this case, as a target, the plane didn't really present a simulation of an enemy aircraft. However, ground troops could fire away at it and presumably learn something before it was blown away. Something altogether more developed in the way of drones was to appear during the Second World War. Constructed in Germany, Hitler's terror weapons led into action by the V-1. This was not a rocket, it was a pulse jet-powered pilotless aeroplane, which carried a 1-ton warhead. It was 23 feet long and had a wingspan of 17 feet. Over 30,000 were produced, and over 8,000 were actually launched against the cities of Britain. The V-1 was relatively slow, with a top speed of 400 miles per hour, and nearly 4,000 of them were brought down by fighters or anti-aircraft artillery. Captured V-1s started to come back to the US for testing and evaluation as soon as they were available, and they were given intense scrutiny by scientists working on the equivalent American programs. Soon, the US started producing its own copy of the V-1 in significant numbers, and testing took place on a number of the aspects of missile design and use that have marked the post-war years. Included in these tests with the American V-1s were firings from submarines that are very prophetic, even if they look a little ridiculous. During the war, the US had also worked on unpowered bomb carriers, glide bombs, which were radio-controlled by the bombardier in fall. Another avenue of remote-controlled drone experiments employed what were, for drones, very big aircraft. Referred to as Weary Willies, old bombers which had passed their life expectancy were retired in a very dramatic fashion, being packed with explosives and then flown by remote control into a target. But not all military drone development has been to do with flying bombs. There have been several major advances in battlefield scout drones. This little observer, armed with television, was developed to give infantry a wider area of search and some knowledge of what was happening across the battlefield without risking heavy casualties in scouting and reconnaissance. Vietnam saw the deployment of a number of drones in several important roles. With the North Vietnamese armed to the teeth with the most advanced ground-based anti-aircraft defences ever tested in warfare, flying over the north became increasingly risky, and the little pilotless planes performed important reconnaissance and electronics suppression missions. Between 1965 and 1975, over 3,000 missions were flown by the remote piloted vehicles, and over 200 of them were actually shot down, which could have been 200 two-man reconnaissance or wild weasel aircraft. These things saved lives. The reconnaissance drones, flying quite low at 500 miles per hour, could get away with sweeps over the most highly defended areas. Their electronic countermeasures brethren would fly in dispensing chaff and using powerful transmitters to jam missile site radar guidance into uselessness. They'd fly in ahead of a raid, clearing the way. After a mission, the drones would be directed back into friendly airspace and there be retrieved by helicopters in a maneuver that could be difficult and dangerous. The 3,000-pound drones proving sometimes to be uncooperative and unwieldy. The drones in Vietnam point the way to some of the future options on the battlefield. Already there are drones that deploy their own drones in the form of tank-hunting scouts and the missiles they can fire. If they're as effective as those drones used in Vietnam, they will be formidable indeed. One other interesting story about drones, or rather flying bombs, concerns the Tor. This was actually a pretty unsuccessful private piloted plane design. The manufacturers managed to interest the Defense Department in it for use as an anti-shipping weapon. The mutation used television and radio controls and was quite sophisticated in a lot of regards. After training, it was possible for an operator to pilot the planes quite proficiently, using the hazy television images. Interestingly, at the end of the war, some enterprising bargain hunters bought up surplus Tor mutations very cheaply and transformed them back into piloted private planes. The mutation of aircraft is almost constant. Most types go through several generations in the course of their production lives, as responses to faults or as improvements. There are mutations that go into production, or there are one-off test aircraft which study particular adaptations. Hence, a B-17 Flying Fortress with inline engines, or a P-47 Thunderbolt with counter-rotating props. Another area of mutation is not specifically dedicated to the type involved. For example, the response to the experience of fighters in mud, with accidents and curtailed activity. This saw testing of different undercarriage for use in muddy conditions, which should be seen as not only applicable to the fighter type used in the tests, but to all fighters battling in mud. A further level of mutation can be seen as the development of characteristics of a particular plane into a completely different plane. A lot of the painstaking and expensive theoretical work carries over from one design to another. Although the derivation may be seen as superficial, the famous P-38 Lightning, one of the war's best fighters, was very influential on the development of another aircraft. This was the much bigger twin-forked Devil from the Lockheed stable, the Chain Lightning XP-58. This plane was conceived as a fighter-destroyer, in a role very similar to that of the German Messerschmitt 110. The Chain Lightning was also developed later to be used as a long-range escort fighter, in a basic enlargement of the Lightning. But in this, it proved to be too stolid to engage successfully in dogfighting. Plans were then redeveloped to see it in an anti-shipping role, but enthusiasm was waning, and though it could probably have been successfully deployed as an attack aircraft, it was not proceeded with. The legacy of the P-38 is evident throughout the layout of the Chain Lightning, with notable changes in scale, propellers, and the inclusion of a second crewman in a turret at the rear of the fuselage. With a top speed of 436 miles per hour and a cruising range of 2,650 miles, the XP-58 had quite good performance for its day, but it was simply too heavy to be adequately maneuverable. Another type of mutation altogether appears when an aircraft is used as a test bed for technology being developed for a new type, as here with a B-26 being used to test the undercarriage under development for the B-47 jet bomber. However, the most interesting mutations have occurred within the same type, with the growth of a plane to fill new roles or to use new technologies, or simply to rectify things that were not right with the original design. When the English electric Canberra was selected as the B-57 for the United States Air Force, the Martin Company was contracted to build the British plane in the US. The Canberra, though fast and manoeuvrable for a bomber, had some very idiosyncratic design features, not least of which was the strange positioning of the crew, which made it highly unlikely that the bomb aimer would be able to escape the plane in an emergency. This problem and other limitations of the Canberra were resolved by Martin over the next year, and various improvements on the original were incorporated in the following models. These included Martin's revolving bomb bay and a welter of new equipment to turn the bomber into a night intruder and a reconnaissance plane. The B-57 went on to play a minor but very successful role in Vietnam. However, the mutation of the B-57 did not stop there. The development of the U-2 high-altitude reconnaissance intrusion aircraft was delayed, and as an interim measure, it was decided to develop an enlarged wing for the B-57 to enable it to fill the gap. Accordingly, what came to be known as the B-57D big wing aircraft took to the air. With a wingspan over 40 foot longer than the original bomber, these planes not only filled the gap while the U-2 was sorted out, but complemented it when it had been introduced, being able to carry a greater load and hence conduct missions that the U-2 could not, especially in electronic information gathering. However, there were major problems with the stresses on the wing spar, and the wings themselves proved to have very limited life expectancy. Later, emphasizing how valuable the B-57D had been, a further development, the B-57F, took to the air with a wingspan that was now a further 20 foot wide, only 6 foot short of twice the original Canberra span, and these mutants performed very well at extreme heights. Perhaps the most impressive range of mutations ever developed from one aircraft type would be that large family of planes that are based on the Boeing B-29 Superfortress. This plane was the ultimate big bomber of the Second World War and carried over to bear a large load in the Korean campaign. The four-engined Superfortress built an enviable record in its original task and was the critical weapon in the reduction of Japan, maintaining a strategic campaign that wrought tremendous damage and brought World War II to a close. When they became outmoded, some of the B-29s were converted by the Air Force to use as aerial tankers and continued in their new role as KB-29s for quite a few years. There were heaps of spares and mothballed planes to be cannibalized to keep them in the air. Here, one of them refuels a mutation of the B-29, the B-50, which had bigger engines, a strengthened wing, and a new tail that was so tall it had provision to fold it over so the plane would fit into the hangars. In a further mutation, some of the B-50s were fitted with auxiliary jet engines to pep up their performance when they too were passed on to the role of aerial tankers. This was essentially so that they could travel at speeds above the stall point of the fighter aircraft they were refueling. The matching of jet fighters with piston-engined tankers was a difficult process, and while the KB-50s were successfully employed, as far as the fighters were concerned, they were far from ideal in their new role. The B-50 shared much the same fuselage as the B-29, but the actual cargo variant of the Superfortress was a very different-looking plane. The C-97 had a completely different fuselage, with the look of being two fuselages, a new fat one superimposed on a remnant of the B-29 shape. Needless to say, the C-97s didn't take long to develop a tanker version, as the mutations of the original plane continued to proliferate. The most glamorous of the Superfortress variants was the Stratocruiser, Boeing's 1940s version of what a long-range passenger aircraft should be, luxuriously appointed and spacious with a bar downstairs. But the Stratocruiser wasn't a raging sales success, and old age was catching up with the whole line. And after a while, the B-29s, B-50s and the rest were congregating at the wrecking yards, ready for scrapping. But for some of the C-97s and Stratocruisers, their bulging fuselages were to see them given a new lease of life. A company called Aerospace Lines, working on that commodious fuselage's basic virtues, started to build wildly distended hulls onto the planes to carry specialist cargo, including spacecraft, aircraft, rockets, and other large, fully assembled pieces of hardware. These aeroplanes with goiters have proved very successful since the first one was built in 1962. The massive lobes allow fuselage heights which started at 20 feet and have now progressed beyond 25 feet with a cargo hold of over 39,000 cubic foot capacity. The later model Super Guppies, built to carry round components for the Saturn rocket program, have turboprops rather than the original piston engines and have a nose section that opens out for easy loading. Here, two of the experimental lifting body shapes, the X-24B and the HL-10, are loaded into a Super Guppy. It's difficult to imagine that there will be many planes which will undergo not just the number of variations that the B-29 has seen, but the absolute transformation that has occurred with the plane. After all, the B-29 was a model of super streamlining. Nothing bulged from that clean shape unnecessarily. The functional demand of the mission dictated a strict discipline in its smooth lines. So where did this great bloated whale with its puckered brow and lack of scale come from? The Douglas B-66, the Air Force version of the Navy A-3D, was first deployed as a tactical jet bomber by the US in 1955. It had a fairly long career, seeing a lot of service in Vietnam in electronics countermeasures and reconnaissance roles. Starting in 1961, two of these planes were rebuilt by the Northrop Company to be the X-21A experimental aircraft. Their peculiar camel hump and new wing were part of a determined assault on one of aviation's most enduring bugbears, the drag caused by disturbed air around the surface of a plane, particularly the broad surfaces of the wing, where undisturbed air would offer better lift and such reduction of drag that very meaningful fuel savings could be made. The idea being tested was to suck the air from the surface into the wing and then force it out the rear, effectively removing the turbulence and allowing smooth airflow. The basis of this was a porous wing surface. The system was refined to a testable condition for the first time for the X-21A program. Ultimately, the test series was to prove two things about the idea. Firstly, that it worked, and secondly, that it was wildly impractical. The maintenance required to keep all the passages in the wing clean and working, not to mention the holes in the exterior, was simply impossible. There were no less than 815,388 metering holes and 67,944 tributary ducts in the wing. And the fact that the thing worked did not in any way change the fact that it was so expensive and hard to maintain as to be totally unusable except in experimental situations. Stretching the idea of mutations a little further, there have been planes that are designed to adopt different shapes to order. One such case being this little Boeing spotter plane. With impressively short takeoff and landing and an almost impossibly low stall point, a functional little battlefield plane with a variety of roles to play. But when it was not in the air, this little plane had another trick. It was the work of only a few minutes to fold back all the protruding wings and other aeroplane bits, and it mutated into a trailer, ready to be towed off by a jeep. The designers had done a complete job. There were restraints for everything, and everything worked neatly. An excellent and practical approach to the tactical need, even if there is something a little unnerving about the idea of a plane which boasts as virtue that it folds up. Probably even more unnerving is the thought of a plane that arrives in a bag, totally collapsible. The Goodyear company worked this one out, a winged powered balloon with the most rudimentary looking control arrangements, which, despite their appearance, worked, providing a portable miniature spotter plane. As an example of the challenges that face designers of aircraft and their various ways of approaching answers, the matter of ultra-lightweight, single-person, practical, portable air vehicles is illuminating. Here, the designer can resort to virtually none of the huge body of knowledge that guides aviation. There's no way that you can start with the normal premise of a wing and work up from there if the user has to carry the thing around with him when it's not in use. Hence, a lot of arrangements for screwing pipes together, inflating rubber planes, rocket belts, and other ideas have surfaced. The powered hang glider being possibly the most effective development to date. There's a sense of adventure about these kinds of aircraft, and the designers have worked long and hard to reduce flight to the barest minimum needed in producing them. A lot of people fantasize about flying in such personal transport, and a lot of people nowadays do it with kits they build in their garages. To date, it's difficult to see which will endure. Presumably the hang glider, which is simple and effective and looks good enough as design to stick around. Good design does endure. The Pitt Special, designed in 1944, an anachronistically biplane, has remained one of the best aerobatic planes in the world ever since. The intended role informed the designer so successfully that the choices he made then are still right now. Hitler's designers, working on his experimental planes and terror weapons, were following trails that have led in many cases straight to the modern day. The Germans built and tested many of the theoretical assessments of their designers, and the list of firsts associated with that intensely concentrated period of research is pretty staggering. After the war, of course, this research and the researchers themselves went into the service of the two developing Cold War camps, and their work went on being refined. In matters of rocketry and remote-guided missilery, they made a number of significant advances, sorting out reliable power plants for their missiles and sorting out stable and controllable shapes for the whole contraptions. The Germans also made notable advances in control systems, in both radio control and in jamming-proof wire-linked controls. Presumably, with a system like this, it took some time to train the operator up to skillful guidance of the missiles. However, tests that were conducted showed the systems worked well, certainly well enough to have been a nuisance to have prowling about and a definite menace to shipping. The extensions on the rear of the wing of this model are for wire spools, physically connecting the missile to its controller in the parent aircraft. This missile, the HS-293, was used with both control systems. The wire link system requires miles of wire, spooling out from both the missile and the aircraft in 2 strands. This gave the controller a direct link to the missile and precluded any jamming of his control over it. The HS-293 developed into a more powerful version, the 294, which employed 2 rocket engines, otherwise being pretty similar, what we would call an air-to-surface missile. The Luftwaffe also put money into the development of air-to-air missiles for use against the big Allied bombers. In this case, the missile again used wire linking, but this time it's designed to rotate in flight, winding the wires around one another as it went. It was designed for use with any of the planes employed as night fighters, and probably with the day fighter forces as well. The Germans would perhaps have been better occupied in manufacturing more of their jet and rocket fighters, which with heavy cannon could have cut swathes through the bomber forces. But the concept has, as we know, been refined constantly since the war, and their pioneering has become the dominant air-to-air attack format. There have been times since the war when it's been widely believed that manned aircraft were all outmoded, and the air would be, in terms of aerial warfare, totally the domain of the missiles, with intercontinental missiles to replace strategic bombers and a range of other missiles to replace everything else except transport and passenger planes. After all, it was reasoned, it wouldn't be safe over a battlefield in a manned plane. In fact, it may not be safe anywhere in a manned plane if the balloon, as they say, went up. What, of course, they overlooked is the phenomenon of machine stupidity. The smarter robots become, the narrower the theoretical gap between human mind and computer becomes, the more evident the complexity of animal intuition and intelligence becomes. Most of the guidance systems of missiles have at one time or another been subverted by interference, distraction, or blinding, and the missiles, most of the time, don't even know they're being fooled. From the early Gorgon onwards, the US has been the post-war leader in missilery. There have been times when the Soviets have managed to stolidly produce large numbers of their missiles, but the technological edge and sophistication of the United States hardware has been maintained. Along the way, there have been some spectacular successes and some equally spectacular failures. During the last 4 decades, the proliferation of missiles and drones has been astonishing. Today, stockpiles of missiles are enormous. And with the thawing of global relationships, it's noticeable that both of the superpowers are concerned to redress the situation. Both wary and cautious about leaving themselves exposed, but equally aware that the acronym MAD is descriptive of the situation in two ways, as it was intended and as it is obvious. That today's missiles are an insane reality to tolerate is not to belittle the reasons for their development. In a world confronted by Joseph Stalin, the idea of the largest and nastiest possible protection has undoubtedly a lot to recommend it. Nor should distaste for the weapons in any way lessen the achievement of those who designed and built them. These things have represented a massive challenge to their creators, and along the way, they've hurried the development of computers and many other electronic advances. Their guidance, piloting, and target-seeking skills have required and still require constant breakthroughs, constant overtakings by countermeasures, and then further advances. Missiles have created their own merry-go-round of development, increasingly sophisticated, increasingly capable. They are the subject of the work of some of the most brilliant minds of the era, and their side benefits to science and technology have been enormous. For the scientists, they have provided a breathtakingly rapid ride into a digitalized world, an exacting and exact series of tasks. With a missile, there's no pilot to correct for deviation from desired performance during testing. If it doesn't work perfectly, it doesn't work at all. The highest state of refinement of missilery to date is the cruise missile, ground-hugging and, for the moment, virtually unstoppable. We can hope that, if the signs in Eastern Europe have any long-term substance, the cruise missile will be the last generation of this craziness, and the world will be able to thank the missiles for three things: for their contributions to science and aviation, for their contribution to peace over the past decades, and for disappearing. The familiar sight of the space shuttle, one of the major technological achievements of our times, here trundling about with a temporary tail cone. The shuttle is an outstanding aircraft in many respects, not only in the unique capability to fly outside the atmosphere. It could be described as the world's largest and heaviest glider, as that's what it spends a lot of its time inside the atmosphere doing. Here, in 1977, the prototype is being readied for its test flights, if that's the right word, where it will be hoisted aloft, piggyback, by a specially converted Boeing 747. The first thing to do is to hoist the shuttle up the massive tower in what is its least dramatic method of getting off the ground. Very slowly and carefully, Enterprise is hauled into the air. With the shuttle ready, the 747 can be nosed into position. Mating the two giants has been meticulously planned, and the seemingly leisurely pace of activity masks the great care and precision involved. The 747 had been purchased second-hand from American Airlines and had then been flown to the Boeing plant, where it had been modified for its unique missions of ferrying the orbiters to and from various facilities and releasing the prototype for approach and landing tests. Enterprise is inched down onto the cradle braced into the fuselage of the carrier. The delicacy of the operation is disguised by the scale of the components. Edwards Air Force Base, site of NASA's Dryden Center, has seen some very strange and exotic aircraft. However, the giant 747 with the shuttle mounted on its back must rank with the odder sights seen there. With the coupling successfully carried out, what remained was to get the configuration into the air, to prove that it would fly, and to demonstrate that the testing and ferrying flights were feasible. At takeoff in the test series, the assembly weighed in at 260 to 280 tons, relatively light for a 747. But the external load, with the consequent drag and turbulence, provided a completely different set of parameters for the Boeing's performance. The tail cone covering the area of the three engines on the orbiter had been specially designed and constructed by Boeing to be fitted for ferrying and in all but two of the testing flights. The fitting was to neutralize the aerodynamic turbulence from the shuttle's blunt tail, which would cause undue vibration in the aft of the 747, simultaneously creating excess drag. With the bulk of the shuttle mounted on the back of the 747, the airflow to the normal tail fin was disrupted, and the Boeing would have been uncontrollable without the addition of two vertical tail fins to the horizontal tail surfaces. These had to be strongly braced, as they would be subjected to enormous turbulence, particularly in the tests of the shuttle without the tail cone. The two fins restored adequate directional stability to the combination as the pilots prepared for the shuttle's first free flight, and the big Boeing nosed over for release.
905 and Enterprise, Houston is go for pushover.
905, coming to launch heading.
Houston copies.
2, 1, pushover.
Houston copies pushover. 1.
With the combination in a shallow dive and picking up speed, the pilots on the orbiter readied for separation.
Okay, Okay, we are armed. 2 lights and the orbiters go.
250.
Houston is go for set. Have a great flight.
And we'll stand by for the bang, Gordo. Power. Wasn't too bad.
Okay, pitch up.
We're up. Got a
Okay, we got
alarm.
a computer light. It's number 2.
Okay, we got a GPC light, lots of sync on 2, pushing over.
And a big X on computer number 2.
Roger, we understand.
We're going to get a message.
Yeah, that's a definite lurch.
Sideways lurch, just like they said. Okay.
Enterprise, you're clear to start to turn.
Okay, Gordo's in the turn. It is really tight, Bo. In fact, I think it's a little better than the old STA field.
Yeah. Got a steady auto land. 900.
Armed. Okay, we're armed and clear.
Standing by the gear.
200 feet, 290. Okay, the gear is coming down at 270. Coming down.
Mark.
Gear coming.
Doors open and they're all down. Some are down. Look down here. 50 feet. Okay, 3 down. Gear's down. 240. 230.
20.
220. Lots of space.
10.
Beautiful.
Holding 10.
210.
220 at about 5 feet.
210.
4 feet. Getting some dust.
200.
3 feet. 2 feet.
195.
Just overlap about 2 feet.
185.
You're on. You're on.
Okay, speed brakes. Speed brakes are coming.
About 10 feet.
Speed brakes are halfway up.
We'll see you, babe.
Okay, I got 130 knots.
Okay, it's great.
120.
5 minutes and 21 seconds later, the flight was over.
Okay, 80. Okay, 60 knots. Try the nose well.
Okay, that was too good a glider.
It had been intended to conduct a series of 5 flights with the cone on before a further 2 flights with the shuttle's blunt tail exposed. But after 3 extremely successful flights, it was decided to shorten the series and fly the shuttle without the cone immediately. The exposed rear of the shuttle presented real turbulence problems for the 747 pilots for the first time in the series. And the specially modified tail of the Boeing was buffeted and shaken, as here on the second coneless flight, the last of the glide and landing test series.
230 knots. Stand by for launch ready, Joe. Set. Okay. Body prep set. Good. Okay, pushing over. Okay. Okay, Joe, we're configured. Beautiful. 180 knots. Orbiter gear. Okay. Get the gear. Gear's coming. Okay, 200 feet, Joe, 260
Despite a small miscalculation from the pilot, which meant that the landing was a bit bumpy, touchdown was made safely and the series was closed. Now, the shuttle program could move on to its greater task, to conduct its series of space missions. It had originally been planned that the shuttle would be a combination plane, parasitic on its larger carrier until release from the atmosphere, with the other part returning to land. Many concepts based on this specification had been delivered, and though they should have proved cheaper to operate than the large rockets that are used in their stead, the thought of the development costs associated with such a project was enough to ensure the idea was short-lived. Certainly the shuttle development itself was a long and expensive business, and the development of a bigger twin for it may have caused the demise of the whole program. In being born as a parasite concept, the shuttle reflected a design objective that has a history going back to the earliest years of aviation. It could perhaps still be described as having a parasitic relationship, with its huge unpiloted rocket engines and propellant tank.
Vince 03. Vince. 0. +1, +2, +3. Get back. +5, +6.
102, flight liftoff confirmed.
Back, roll program. Go.
Roger, roll. get a status, Fido. Go. Booster, go. GNC, go. Eagle, go. Go at 40, Capcom. Columbia, Houston, you're go at 40.
In the era of the great airships, there were several examples where large rigids were designed to carry aeroplanes. With their immense size and lifting power, the airships could provide internal spaces so that not only could they launch aircraft, but they could also land them and service, refuel and redispatch them. The outstanding examples were the US Navy's Akron and Macon. 785 feet long and capable of 75 miles per hour, they combined the reconnaissance capabilities of earlier airships with the fact that they were also aircraft carriers. They had hangars in their bellies for 5 Curtiss fighters, which were launched and retrieved in mid-air by means of a trapeze lowered through the hull. With a load-carrying capability over 160,000 pounds, the Akron and Macon were not stretched by having to cope with the needs of the little planes, and thousands of successful flights were made from the two giants. Even today, when new proposals for airships are mooted, this plane-carrying ability is one of the virtues of the giants that is recalled, and there are undoubtedly some applications to which such craft could be put. Back in the heyday of the airship, it was probably inevitable that attempts would be made to use them as aircraft carriers. Though the British, Germans and others used the idea to varying extents and with varying success, it was the Akron and Macon which carried the idea to its most advanced manifestation. The fragility that the Akron displayed on this occasion was an indication of one of the reasons for their passing from the skies. But at the time, airships had a major advantage over aeroplanes in that they could travel over very long distances and were capable of regular transatlantic flights. Schemes to deploy planes from other planes had been limited to examples like this early 30s Russian experiment to launch fighters from the big TB-3 bomber. Of course, there was no way that the big plane could practically retrieve them after takeoff. But the primary aim of this and other similar military experiments was to conserve the fuel of the small plane until it was needed. This was also partially the intent with the British company Short Brothers Mayo Composite Aircraft, the brainchild of Imperial Airways Technical Chief Major R.H. Mayo. This involved mounting a small 4-engined seaplane onto a C-class flying boat, using the bigger plane's fuel and engine power to lift the actual payload-carrying seaplane into the air. Once aloft, the two components separated, the flying boat returning to base, while the upper plane, loaded to a weight which would have precluded a takeoff under its power alone, continued on its transatlantic journey. The planes involved in the trials of this idea, named Maya and Mercury, made their first actual separation on the 6th of February 1938. In July, the Mayo combination succeeded in sending off the Mercury on its first transatlantic crossing. But the idea was never pushed much further than an experimental stage, though it had undoubtedly posed one successful solution to the problem of long-range flight. It was to a more sinister purpose that German wartime designers evolved a similar configuration, using the Junkers Ju-88 twin-engine bomber and the Messerschmitt Me-109 fighter. This was given the combination name Mistel or Mistletoe. Both of these planes had served their masters well and were readily available. For example, over 30,000 109s had been produced. With the Mistral composite, the nose of the Junkers became a large explosive charge. With the engines of both planes providing power, the pilot, sitting in the fighter, would fly the combination to the target and then set the bomber, or more exactly the bomb, to glide to a spectacular and destructive end. Mistral combinations were used against the Allied Normandy landings without much effect, but their successful deployment encouraged the Germans to build more. Only 15 of the original Me-109 combinations were used, but over 250 using FW-190s were constructed and used in the later stages of the war. A number of minor successes were attributed to them, but given the straits that the Reich was in by that time, the fighters could have undoubtedly been better utilized in their more normal role. It had been these two fighters that had been the rock upon which the Western Allies' strategic bombing had almost broken. Their strong and sustained defense had seen losses in the Allies' bomber fleets reach unsustainable proportions, and it had only been the development of the long-range escort fighter, in particular the Mustang, that had seen the tide of the air war slowly turned against the Germans. The attrition wrought on the Luftwaffe, particularly in terms of pilots, had meant that the bombers had enjoyed relative immunity from fighter attack, though the by then outnumbered German planes had still managed to courageously attack the massed formations into the teeth of the defending escorts. Given the Luftwaffe's practice of trying to avoid or ignore the fighters while attacking the bombers, they were almost easy prey for the Allied fighter pilots, and the bombers came to be in much greater danger from the German anti-aircraft artillery than the attacking planes. Too late and too few to stem the tide of the war, the Germans eventually deployed the stunning new force of the jet-powered Me-262. They were to have limited overall effect on the conflict, but their ramifications clearly spelt the demise of the theory of strategic bombing, at least using piston-engined planes. The speed of the new jets meant that they were able to simply elude the fighters and get on with the creation of havoc in the bomber formations, while the heavy demand for fuel of the early jet engines meant that the Allies could not deploy a long-range jet escort against them. The British had actually commenced mass production of their Meteor before the German commitment to the Me-262. And in trials with American B-29s, the message about the jet's impact was reinforced. Clearly, long-range operations by piston-engined planes were not possible against a defending force of jets. And, in the absence of escorting jets, all theories of long-range operations were no longer valid. To commence such a campaign would be to set up a turkey shoot for the jet fighter pilots against both the long-range bombers and their piston-engined escorts should they care to become involved. To add urgency to the problem was the knowledge that the Russians, who by now were being identified as the strategic target of the future, were already deploying their first jet fighters. Clearly, something had to be done. And what seemed obvious was that if the escorting jets could not carry enough fuel, then the bombers should carry the fighters themselves. The tricky bit would be that they would also have to carry them back, and landing a winged plane onto another was till then strictly the realm of the barnstormer and stuntman. The McDonnell Company were given the job of developing the proposed fighter, and they came up with the XF-85, known as the Goblin, but widely referred to as the Bug. It was designed as a partner for the giant B-36 bombers then being developed, and was to be deployed from the bomb bay of the mother ship. Essentially, the XF-85 consisted of a jet engine with the pilot sitting astride it. The rest of the plane was occupied by fuel, except for the gun installations. The bomb bay was 16 foot long, so the plane was designed to be 15 foot long. Its 21-foot span reduced to only 5 foot 5 inches when the swept wings were folded up. And even in that position, the plane was only 10 foot high. Instead of landing wheels, there was a retractable hook for the trapeze of the carrier plane, and the tail span was reduced by dividing the tail into 6 odd-shaped surfaces. The engine was a 3,000-pound thrust Westinghouse, and the plane carried around 30 minutes of fuel. It was supposed to have a top speed of 664 miles per hour, but was never to approach that mark in practice. It weighed only 4,550 pounds fully loaded, carrying 130 gallons of fuel. On the 23rd of August 1948, the Goblin flew for the first time. As the new B-36s were only just coming off the production line, the test series was to be conducted with a B-29 acting as the mothership. The B-29 was unable to fully retract the Goblin, but apart from this aspect, the compromise arrangement was much the same as it would have been with the new bomber. Hoisted into the bomb bay from a specially dug pit, the Goblin protruded below the carrier as they taxied to takeoff. With the trapeze restraints on the nose released, the Goblin swung gently for a few moments, then dropped into free flight. If one looks logically at what was being done here, it's not hard to see that falling off the bomber was going to be a lot easier than creeping up into its turbulence to hook back onto the trapeze. This is not only going to be a difficult operation to perform, it's going to be a very dangerous one. Having failed on his gingerly first attempt, the pilot, Edwin Schock, then tried a more highly powered approach. With almost fatal results, as he crashed violently into the trapeze and plummeted away out of control. With the canopy smashed, Schock made an emergency landing on the plane's skid. He had been lucky to escape from the incident, and the plane was carted away to be fixed. In October, the trials resumed, once again with the B-29 as the mothership. The pilot of the XF-85 was in constant contact with the operator of the trapeze in the carrier plane. Once again, the little plane was lowered and the pilot started his engine and set his flaps for takeoff. With the nose stabilizer raised, the pilot had only to slowly advance the throttle to first neutralize the drag on the bomber and then take control of his mount. The stability and control characteristics of the XF-85 have been described as entirely unsatisfactory. And considering that they were only ever flown by an extremely experienced and wily test pilot, it's certainly a good thing that they were never produced in large numbers for use by men of lesser expertise. The business of rejoining the mothership remained as we described it earlier, difficult and dangerous. The test pilot, Edwin Schock, who flew the Goblin in its trials, never managed to get the little plane above a speed of 362 miles per hour. And the two Goblins accumulated a total flying time of only 2 hours and 19 minutes between them. McDonnell's design team proposed a more conventional plane as an extension of the idea, but this was never proceeded with. That there were successful dockings and no fatal accidents is a tribute to the pilot involved. But only 2 XF-85s were built, and they passed deservingly into history. They had been an extreme design demand and were really always only theoretically possible with the knowledge and technology available. The fact that a plane was created that could actually perform the task at all is pretty astounding in itself. With this experience behind them, the Air Force now had a pretty good idea of what it was up against, and the idea of a tiny, specially designed inboard plane was abandoned. The next time the idea surfaced, the plane was basically a standard F-84, coupled as much as was possible, and the procedures had been rationalized. Over the course of the project, the trapeze on the bomber and the hooking contraptions on the RF-84 were to go through various mutations in sorting out a workable proposition. The motherships were GR-B-36 bombers, but the purpose of the arrangement was reconnaissance. The system would allow for the jets to be carried long distances, sent in for high-speed missions over targets where the B-36 would have been a sitting duck, and then retrieved. It could be refueled by the B-36 and sent on another mission if such were needed. In the early trials, even separating could be difficult, but the efforts of those working on the scheme were to be repaid. The process, called FICON for fighter conveyance, was actually adopted, and 25 RF-84s were operationally linked with 10 adapted B-36 motherships. This was to be abandoned after only a year. A takeoff like this was rare. More commonly, the planes would link up once they had both taken off individually. This was done as, carrying the RF-84 at takeoff, the B-36 could not retract its wheels. The fighter's wings were in the way. Once again, the little plane's pilot was in constant contact with the trapeze operator inside the carrier, upon whose care and attention so much depended. Adding the 1,100-mile radius of action of the RF-84 to the potential 2,800-mile ferrying trip made the concept very attractive. But the practical difficulties of the task made its permanent adoption into USAF practice improbable from the start. The idea of the operational parasite, though cumbersome, had posed very particular demands upon the designers of the systems. And, particularly with FICON, the response had been surprisingly successful. McDonnell's Goblin had been perhaps an overly ambitious project, but even so, they had performed a minor miracle in getting as far as they had. Two advances had made the roles of systems like the Goblin and FICON redundant. The jet age had grown rapidly, and the limitations of the early engines had largely been overcome. In addition, advances in electronic countermeasures and suppression were making long-range bombing operations relatively feasible again. FICON's reconnaissance roles and the implicit tactical nuclear weapons delivery the system could have allowed went to new planes designed specifically to cope with the demands. And the job of protecting the intrusion of the giant B-52 over hostile airspace went to tiny Quail drones. Simply described, these were midget aircraft packed with electronic trickery, which were dropped away from the mothership to delude and distract the enemy's weapons. The things emitted larger recognition symbols than a host of B-52s and would thoroughly outwit the electronic tracking and targeting systems of air-to-air missiles fired against the bombers. A single Quail would look to a radar operator like a fleet of incoming bombers and totally overwhelm the less sophisticated guidance of a missile. Theoretically at least, and probably in practice, the Quail made long-range intrusion into hostile airspace achievable again. The B-36s never got to carry Goblins or F-84s into action. The operational cartage the big bombers were given was in carrying the prototype B-58 Hustler to Muroc for testing. The Hustler, the first supersonic bomber, reflected the leaps forward in development that had seen the parasites made redundant. The designers were effectively saved from having to try and develop further systems that involved the ability to launch and retrieve parasites. However, though they were relieved of that cumbersome and demanding specification, there was another group of parasite planes which achieved outstanding results for the engineers as they gnawed away at the limits on practical flight. Once again, it was the Muroc base that saw these planes in operation. They were the X-planes that were in a sequence of dramatic test series to smash the barriers on speed and make the names of their pilots into household names. First was the bullet-like X-1, whose shape reflected the fact that bullets did fly faster than sound when very little else about the sound barrier was known. Aeroplanes approaching Mach 1 had encountered problems of compressibility that had torn them apart in mid-air, and there were many who believed that the sound barrier was an absolute limit on the potential speed that could be attained. On October the 14th, 1947, on this historic flight, Chuck Yeager became the first man to fly through the supposed sound barrier. The design team leader, Robert Woods, though favoring a jet, had been forced by the limitations on the availability, reliability and power of the jets of the day to settle on a rocket-powered plane. And the limitations of the available rockets had further decreed that the plane would not be able to carry sufficient fuel to take off normally and still be able to carry out the mission. It had, therefore, to be air-launched from a mother plane. The congratulations due to Yeager should also be given to Woods and the designers. Where the X-1 had been absolutely flat out at 1.45 times the speed of sound, as Chuck Yeager had demonstrated, the next of the X-planes, the X-1A, was developed to fly past Mach 2, the next logical step in investigating various aspects of ultra-high-speed flight. On this flight, on December the 12th, 1953, Yeager first took the X-1A past Mach 2, then pressed on, achieving almost 2.5 times the speed of sound before encountering the phenomenon known as inertia coupling and losing control of the plane. As you will see, the plane's behavior became violently disrupted, and Yeager, semi-conscious after being thrown about the cockpit, was lucky to regain control eventually and bring the plane safely back to land. During the period between the plane going out of control and Yeager finally managing to stabilize its flight, it had fallen over 40,000 feet. When the problem had been encountered, he'd been traveling at 1,612 miles per hour. And after studying analysis of what had happened, the Air Force imposed an embargo on further X-1A flights over Mach 2, concentrating instead on research into high-altitude flight. Based on research both in wartime Germany and in American laboratories, it was assumed that controllable flight at higher speeds would be possible with the use of swept wings. Not much was actually known about the idea, and with the limitations of wind tunnels and in the absence of computer models, the only way to test the theories was to build a plane and fly it. Developed from the X-1A, the X-2 was designed to explore flight at speeds and altitudes far beyond those achievable with the earlier plane. It flew only 20 times, but it set several notable marks in a career that was marred by accidents, instability, and eventually fatality. Here, on the 23rd of July, 1956, Colonel Frank Everest sets out on a test that was to set a new speed record, 2.85 times the speed of sound. This was a level only bettered by the plane once, on its last flight 2 months later. Then, in succeeding in passing Mach 3, inertia coupling sent the X-2 out of control at 2,094 miles per hour. The plane was destroyed, and the pilot, Milburn Apt, killed. Colonel Everest, seen here, flew the X-2 on 13 flights. This was the last of those, before transferring to other work. X-2 also set a new altitude record, which was to stand for 4 years, 125,907 feet. Now, this is definitely somewhere in the realm where the distinction between an aeroplane and a spacecraft gets a bit artificial. When that record was broken, however, it was by a plane that would push it out eventually to 354,200 feet, the X-15. The North American company's plane was designed to explore the identifiable problems of space and atmospheric flight at very high speeds. The tentative goals were speeds of Mach 6.6 or greater and altitudes in excess of 250,000 feet. On this flight, on July 17, 1962, Robert White flies the plane to 314,500 feet, becoming in the process the first X-15 pilot to be awarded astronaut's wings. At that height, as the film from White's plane shows, the curvature of the Earth is pretty clear. The X-15's flights were a series of outstanding successes. To list all the achievements made by the plane in terms of technological advances and so on would be progressively both more astounding and confusing. For the designers, these X-planes represent the ultimate challenges, but also provide the most reward. Here, testing the limits of a time's knowledge into the realm of theory, the next day's certainties are established. Upon those, of course, the minds of science will deduce the next theory, and so on. Only 199 of a planned 200 flights were flown. Ironically, in the desert, the last flight was cancelled because of a snowstorm. The X-15 could accelerate not only to great height, but of course to great speed. Eventually, with the external tanks to set it on its way, to a mark of 4,520 miles per hour, set in March 1967. The X-15 series more than rewarded its contributors. The 3 examples built exceeded the goals set. And in the long term, the wealth of information they provided is a legacy that can still be seen in the many contributions it made to the aerospace programs. The X-parasites had a symbiotic relationship with science overall. Since the late 1940s, when practical systems were first developed, there has been another form of parasitism that is a daily occurrence: in-flight refueling. The history of aerial tankers goes back to the early days of aviation, when, in experiments in the US and elsewhere, planes were kept aloft on endurance flights by the transfer of fuel from another plane. In essence, the aim was to provide for long-range flights when there was no way that the planes of the day could carry enough fuel for their inefficient engines. These experiments, involving jerry cans of fuel, hoses and funnels, fell far short of a method that could be employed on a regular basis. In the event, the engines improved, and the planes were made artificially large, the space being provided for fuel loads to allow longer flight times. But there was still a limitation to how much this strategy could be carried without the aircraft becoming ludicrously bloated simply to cart the fuel. There would obviously come a point at which there ceased to be any advantage in carrying more tanks, when the plane became unusably cumbersome and all available space inside it was already occupied with its own fuel. Post-war, there were new causes to make in-flight refueling a necessity, not least of which was the excessive thirst of the first generations of jet power plants. And British and American teams, sometimes in competition and sometimes in cooperation, worked out new systems to provide useful range to the new breeds of jet fighters and bombers. There was no point in saddling a fighter with a large load, as it would then, though perhaps having a greater range, be unable to perform its primary function of being extremely hostile at as high a speed as possible. The F-104 serves as a good example. Designed as an interception fighter, it started life with only limited range requirement. But with the demand that it become more versatile in its mission profile, it became necessary to give it in-flight refueling apparatus, which had been excluded from the original design criteria. Through testing on specially built ground installations, a workable arrangement for the equipment-packed frame of the Starfighter was nutted out. The system at that time relied upon the use of long trailing drogue hoses and the skill and persistence of the fighter pilot. The tankers were slow, barely capable of exceeding the speed at which the fighter could stall and cease to be airborne. In the turbulence around the big tanker, barely holding airflow over his wings, the fighter pilot would fiddle his sluggish and unresponsive plane at the drogue. The system left much to be desired. Looked at with the assistance of 20/20 hindsight, it's easy to say that the process seems overly difficult and dangerous. But the twin problems of the tanker's speed and the drogue's uncooperative flexibility were not to be easy to overcome. It's a good thing that they were, because the experience of Vietnam was to show that mission profiles that saw aircraft cruising to a target area and then using maximum power in short bursts were totally wrong. In the presence of hostile jets, missiles, radar-controlled artillery, and other new menaces, most missions were flown flat out from go to woe, not only stressing the power plants, but causing them to drink fuel at a tremendous rate. Meanwhile, refinements and variations of the system abounded, all being tested and found wanting, mostly for the same reason, that they required the fighter pilot to do all the work, and he was already fairly busy keeping his plane under control. Despite the difficulties, the availability of even limited systems had changed the parameters on what range an aircraft could be deployed over, and hence the system was adapted to all sorts of aircraft, even including helicopters. For the Strategic Air Command, in-flight refueling offered the possibility of theoretically permanent flight. A fighter would always be limited to the endurance of the pilot. Once he fell asleep, that'd be that. But a big plane could carry a spare pilot or two, and with their already large range, topping up a bomber gave it enormous potential. It was in experiments with the Strategic Air Command that Boeing developed a new method of controlling the process, removing the responsibility for coupling from either pilot and giving it to a crewman on the tanker, manipulating a more rigid boom. This was developed as part of the mutation of the Boeing 707 into the KC-135 military variant, and the boom arrangement has since become the practical basis for what is now a routine occurrence. Even today's giant transports are not saddled with excessive fuel cartage. They too rely on topping up their reserves, especially after the enormous demands of hauling themselves off the ground. The availability of the tankers has come to inform the designers' decisions, relieving them of some considerations of storage and allowing them a greater latitude in utilizing the space within an airframe. Virtually all military aircraft of today are thus parasites.